Hello everyone, welcome back to the workshop. And for the final session of the day, we have with us Karthik CS from New York University, and he'll be talking about hardness of approximation and parameterized complexity. So thank you so much for joining us, Karthik. Over to you now.
For inviting me. I've been thinking about hardness of approximation and parameterized complexity for a few years now, and my hope is in these three lectures I sort of convey more of the intuition than what is written in the papers, let's say. And so I want to go rather slowly. And day one is going to be just talking about, there will be almost very little to do with hardness of approximation per se, but more about the setting and the tools required to prove such results, where we'll talk about what are the key problems and for hardness of approximation and parameterized complexity. And in the second day, once we have some intuition for these kinds of problems, I want to sort of then start showing how to create a gap, which is what hardness of approximation is. You start from a problem that does not have any gap and then create some gap from it. So we're going to talk about how to do that. And in day three, once we showed that, like there are a couple of problems for which we can show some hardness of approximation results, how does it imply hardness of approximation for other problems and various applications? So this is basically the outline which I want to have for today's lecture, tomorrow, and day after tomorrow. And in particular about today's lecture, so it has three parts. And I want to sort of first talk about hardness of approximation in NP, because there's a lot of similarities that run, and the intuition is more clear in the NP world. So once I talk a bit about that, then I want to sort of then say, what is hardness of approximation and parameterized complexity mean? What are the problems of interest, and so on. And then second, I want to focus on defining formally two problems. One is called MaxCover and the other one-sided Biclique, and sort of say the connections between them and where they lie in parameterized complexity and things like that. And then the third part will have nothing to do with the previous two things, but it will be a very intuitive introduction to coding theory. And so because the reason we need coding theory is that we need these codes in order to sort of do gap amplification in tomorrow's lecture. So I want to do this first. So I introduce all the definitions, all the problems, all the tools. And once we have some intuition today, so tomorrow I'll recap, of course, the definitions, and we'll see how to use them to create some gap. So let's start with what is hardness of approximation. So in general, the motivation stems from why do we study computation? Because there are a lot of problems, optimization problems, and some of them or most of them are not tractable. That is, you want them to be solved efficiently, but whatever your notion of efficiency is, I don't even want to define it, but it's not tractable, it's not satisfiable. Like you're not happy with the running time of your problem. So a typical way to sort of cope with these things is to design algorithms which don't really compute the optimum value, but something close to the optimum. Say if you had the traveling salesman problem and there is a tour of, say, some opt, then you don't want to get that opt. Maybe you're okay with, say, 1.3 times the opt. So can we get it? Because maybe in reality, it doesn't make much difference. And then the interesting thing is that in most cases, it's not necessary that you can approximate it arbitrarily. So in fact, even in some cases, you can show that finding an opt which is twice far away from the optimum is as hard as actually solving it exactly. And this study of trying to understand, if I'm okay with approximate solutions, how hard is it? Is it as hard as the original problem, or is it easier? This study is the area of hardness of approximation. And it's typically studied in the NP world, but the way I stated it here, it can really apply to any setting. It can be fine-grained complexity, it can be communication complexity. It depends on what your notion of tractability is. And then now let's concretely look at the NP world. And in NP, you want to say that tractability means polynomial time. And intractable is essentially assuming NP not equal to P is showing NP hardness. So you know that certain problems are NP hard. What about approximately solving them? Is it still NP hard? And the foundation of proving such results is the PCP theorem. And I want to state some version of the PCP theorem, and I want to state it in a way that will be used throughout the talk. So I want to introduce what is known as the label cover problem. So in the label cover problem, we are given a bipartite graph. As you can see, you have two partite sets, U and W. So there are n nodes in U and m nodes in W. And there are some edges, So it's a bipartite graph. But for every edge, Ui, Wj, we have what is known as a constraint, which is pi ij. It's just a subset of, so you have sigma u, which is some finite set, and sigma w, which is some finite set. It's just a subset of all pairs of sigma u, sigma w. So it's sort of saying, if what values of u1 do I allow, and when it's as a pair with w1. So that's pi 1 1. And what you really, so this is a problem, right? Like the input to the problem would be this bipartite graph, and for every edge, you're given a subset of sigma u times sigma w. And what you want to find is a labeling for every vertex in the graph. So everything of u, you want to label it using the sigma u that was given to you as input, and everything in w, you want to label it using sigma w as input. A labeling is just giving one alphabet of sigma u to a vertex of u, and one, like an alphabet of sigma w to a vertex of w. So for each of the vertices. And now we say that if you have a labeling of all the vertices, it satisfies a particular edge in your input graph, let's say the ui and wj edge. If and only if you look at the sigma u, sigma w will give certain values to ui and wj, right? So now you look at them, that's a pair in sigma u times sigma w. If it's in pi ij, if it's in one of the accepting configurations, then you say that this edge is satisfied by this labeling. It's as simple as that. So for instance, you could think of 3SAT, and all the u's can be your variables, and all the w's can be your clauses. And you basically, the graph will be defined based on the CNF, which is each clause will be connected to the three variables that appears in it, if it's a 3CNF. And now you can sort of say, I want to give every variable either 0 or 1. And every clause you will get, say, a value between 0, 0, 0 to 1, 1, 1. So based on what the values are. And if there's a consistent satisfying assignment, then you'll be able to give everything values. Otherwise, you won't. So the value of a label cover for a particular labeling is just how many fraction of edges are we satisfying. So in the yes case, if you had like the SAT reduction from SAT to label cover, you'll be able to satisfy everything. So the value will be 1. And the value of the entire label cover is just you go over all possible labelings. And the PCP theorem then just says the following, that the value, if it's either 1 or if it's 0.99, so you have a constant fraction of the edges fading, right? So you won't be able to decide if the value is 1 or 0.99. Deciding this is as hard as solving the exact 3SAT problem. So it's essentially a reduction from 3SAT to this. And so this is the PCP theorem. Starting from this, we are able to prove all these great inapproximability results. The more common unique games conjecture essentially says that pi here are like permutations. So there is more. So you can always put more conditions on how pi is, and that will give you more stronger and stronger NP hardness results. So this is the bedrock of NP inapproximability, hardness of approximation in NP. And what you would want is for parameterized complexity to have something similar to this. So to start with, we need to first talk of problems something like label cover in parameterized complexity. So to do that, I'll retell the exact same problem, label cover, but in what is called the extended formulation. So in the extended label cover, all you have done is that you have blown up each vertex by all the possible labels it can get. So here you took the original label cover you had, but then each vertex on U will become sigma U copies, and each vertex in W will become sigma W copies, each one corresponding to a label that it can get. And now you put an edge between two things. If there was originally an edge before you made the copies, and if now this also corresponds to a pair of labels, right? So if that pair of labels is in pi ij, that if for an edge ij, if you look, then it will be made into sigma U sigma W copies. And now you look at each one of them. If each one of them is accepted in pi ij, then you put an edge. So this is called as an extended label cover. And now the notion of labeling, which you had before was like a function. So assigning each guy a thing. So it's the same thing. Here we do the same thing. We just pick a subset of W such that you pick exactly one from W1, one from W2, so on and so forth. And now a solution would be like this subgraph that you would pick, because you'll pick an S here and a T here. And so you have the subgraph. And notice that if it was if the value of the label cover was 1, then the subgraph will be actually the original label cover instance that you had. So it's like how much of the subgraph can you construct in this extended label cover of the original graph you had. Anyway, so I wanted to just give a feel of this, because we're going to go into more formal definitions soon. So let's start with the motivation for parameterized inapproximability. As we said, most optimization problems are NP-hard. So we have what is known as a coping mechanism. So you want to cope, like you just don't want to say it's hard. So let's try to cope with it. So there are two ways to cope with it. Either you can ask for approximate solutions, or you can say, hey, I have this parameter of interest and I don't mind. And to me, it's like a very small value. So I don't mind running a lot in that. So you ask for fixed parameter tractability. And then the thing is, there are certain problems which are very important, capturing many different applications, and they are very hard to cope. For instance, the set cover problem is a classic NP-hard problem from the early 70s, Karp's famous 21 problems. And set cover is, sadly, you can't even approximate it to log n factor. So giving an approximation algorithm which has a log n multiplicative factor is the best you can do. There's a greedy algorithm that does it, and you can't even do better than log n. And so doing better than log n is like solving it exactly. And on the other hand, fixed parameter wise, if I'm given a set system and I ask k sets that cover the entire universe, this is a W2 hard problem. So it's also believed to be not tractable. So then you can ask the question, what about, I tell you there is k sets that cover the entire universe. Just give me something that's 2 to the 2 to the k. Find 2 to the 2 to the k many sets that cover the universe, because there are k which cover it. And I'm allowing you to sort of find 2 to the 2 to the k many sets that cover the universe. So studying in general, you can ask for any problem, is there an f of k poly n time algorithm, a FPT time algorithm, that approximated to a factor t of k for some computable function t? And so this is the study of fixed parameter approximability, and showing such algorithms don't exist with such running times is essentially the study of fixed parameter inapproximability. Okay, so this is the motivation. And there are a host of results. So I just took this, I didn't want to make this slide because person had it in like last year, and there is just way too many results that we already have. So I just want to go over a small highlight of them. So first of all, there is a lot of assumptions that you can make. So you can make the classic W1 hardness, W1 not equal to FPT assumption, which is that Biclique does not have an FPT algorithm. Or you can make more stronger assumptions like ETH, which give you more specified running times, that 3-sat cannot be solved in 2 to the little of n time. Strong ETH, that k-sat cannot be solved in 2 to the n time, better than 2 to the n time. Gap ETH, where you already assume that gap SAT instances, distinguishing SAT instances which have all satisfiable, an assignment satisfies everything versus every assignment failing at least a constant fraction of the clauses. That cannot be solved in 2 to the little of n time. PIH, which I'm going to come into later. So there's another gap assumption. And from this, we are able to prove, like for many important problems, computational problems, fixed parameter in approximability results. Like some highlights are dominating set, even set, Steiner orientation, K-clique, K-Biclique, directed odd cycle traversal, like max coverage, which leads to then clustering problems being hard to approximate in fixed parameter time. So we have a bunch of results. And my talks are not based on results, but more on technique and intuition. So I'm going to just focus for this series of talks on just showing you almost the complete proof of set cover problem, for the clique problem, and the biclique problem. So these are the focuses that will be there in this talk. And so now that I have said this, let's go to start defining some key problems that we want to study. So one of the problems that we want to study is the max cover problem. And it's going to remind a lot, it's very similar to the label cover problem that was studied, but with a few important differences. So even in the max cover problem, you have a bipartite graph, but here you have collection of nodes called super nodes, which are, say you have on the left U1 to UR, and on the right W1 to WK. Okay, so K is the parameter of interest. So you have a bipartite graph with a collection of nodes on each side. One is called the right supernodes, the other is called the left supernodes. And now, as before in the extended formulation, we have what is called a labeling. A labeling is just picking, labeling for W would be to pick one vertex in W1, one vertex in W2, one vertex in W3, so on and so forth, one vertex in each of the WIs. So this is called a labeling. And now, given a labeling, so once you say, for instance, the red edges that you see, given a labeling where you picked one from each WI, we say that it covers some UI, for here instance U1. If there is a common neighbor to all of S in U1. So S is a labeling, which means you have picked one from each WI, WJ, let's say. And we say that S covers a left supernode UI if there exists a vertex in UI which is a common neighbor to all the vertices in S. So here the red edges, if the vertices picked are the following that you see, the middle vertices in each WJ, then you can see that there is some vertex in U1 which covers all of them, which sort of is a common neighbor to all of them. So this labeling covers this left supernode U1. So this is the notion, this notion of covering that we introduce. And then we can introduce the complexity measure, which is given a labeling of the right guys, what the fraction of the left supernodes that are covered is max cover value. It's what is called the complexity measure of interest. So the max cover value of the labeling is the fraction of left supernodes that are covered by a labeling of the right supernodes. And then the max cover value, the total measure itself, is just you go over all possible labelings of W, right? So you can find the optimum because if you assume that each W1 is, say, of time n, of size n, then you can go over all possible k tuples in n to the k time, and you can check its max cover value and find the maximum. So it can be trivially solved in n to the k time, but can it be done better, like say 2 to the k times poly n time? So the max cover question is essentially just then asking, is there a labeling of the right supernodes, picking one guy from each, such that we can cover every left supernode? Or is it the case that you can at most cover S fraction of the? So now I want to sort of say that max cover is an important problem. So in order to just say this, so let's try to see that it captures many problems. By one way to sort of say this is that we can reduce many problems to max cover. So it has this abstract structure that we need to sort of capture many of the problems that we want. And to do that, let me start off with the most famous problem. That's K-clique. So I want to see that K-cliques can be reduced to max cover. So you can see it as a max cover problem.
Can I
And
ask one question?
yeah, sure.
So, what is the difference between max cover and the version of label cover you previously mentioned, where you had this blown up vertices, right? Where you repeated
Right.
what?
The difference is actually, that's a very good question. The difference is the measure. So in the label cover, which is studied in the NP world, the measure is how many edges do you satisfy. And here it's, we don't care about the edges, but we are caring about the vertices.
Okay.
So it's informally equivalent to sort of saying, you look at the label cover version, and instead of the edges, you look at how many vertices on the one side have all their edges satisfied.
Okay.
And that version is essentially, when you make it a parameterized complexity version, becomes max cover.
Okay. Thanks.
So that was a good question. And so that's an important distinction, because proving the exact label cover version is still a quite challenging task, and we don't know yet how to do it from W1 hardness. But nevertheless, although this version has this stronger requirement, I want to say that it's still abstract enough to capture many problems. So to start with, I want to show that it captures the K-clique problem. So what is the K-clique problem? You're given a graph on n vertices with, say, edge set E0, and you have this parameter K of interest. So the way we would construct then, given this graph G, is each Wj would be a copy of E0. And each Ui would be a copy of n, the vertex set. So we have E0s, all like K choose too many E0s, and K many copies of n. So our parameter is now K choose 2 actually. And when do we put an edge? So the way we do it is that if we think of the labels W1, W2 up to WK choose 2 as all possible pairs, distinct pairs of the set K, right? There are K choose too many things. So we can think of them like that. And now you look at some Wj prime, okay, where J and J prime are distinct. And if Ui, the I is different from both J and J prime, then you just put all possible edges between the two things, right? So there are E vertices on one side, E many vertices, whatever the set size is, and N vertices on the other side, and you put all possible edges between them. On the other hand, if by some chance that you have Ui left supernode and Wj prime right supernode, and I equals to J or J prime, one of the two things, then what do we do is that we actually look at the graph G, and these are edges, these are vertices. So an edge is incident on two vertices, so you put the corresponding two edges. So you make the incidence graph between the two things. And it's very easy to verify right after that, that if the max cover is 1, then you can pick the K choose 2 edges of your graph G, which form a K-clique in G. And you can choose the K choose 2 on W and K on U. And you basically have that labeling of K choose 2 edges gives you max cover value 1. But if there was no K-clique, then regardless of what labeling you take of these K choose 2 supernodes on your right, you will fail at least one supernode on the left. So you can capture K-clique as follows. Actually, now that we are here, let me even say how it will capture K-sum. So let me go back to this. Now, K-sum problem is when you are given K collection of integers, and you want to find one integer in each of the collections such that the sum is 0. It can be done in n to the k over 2 time. And can you do better? We don't know. It's a W1 hard problem. And the way you would reduce it then is actually this very nice trick. which is each W1 would be your A1, like the collection of integers. So you have K collections of integers, that will be your Ws. And your U's will be all possible primes up to some value. And then the idea is just that you have your UI would be looking at all possible K tuple of integers in 0 mod P whose sums to 0. And you put an edge between two guys if this guy mod P corresponds to this value here. So this is a nice exercise for people to verify later that you can actually reduce the K sum problem to MaxCover. And as a hint, you need to use the Leibniz remainder theorem. So you can see that you can reduce K sum. Actually, I would even say it's a nice exercise to reduce 3 like the ETH problem. You can reduce it all the way down to K sum with stronger properties than when you would do with K-clique. So you can try showing that MaxCover cannot be solved in n to the middle of K time, assuming ETH. So these are all very nice exercises to sort of get a feel for MaxCover. But now that I've convinced you that MaxCover is sort of important, let me try to state what do we know about it. So I just reduced K-clique to MaxCover, which means it is W1 hard. But you can actually show, and we will show like in the next slide, that it's W1 complete if the number of left supernodes, the right supernodes is the parameter K, the left supernodes we didn't say what it is, R. So if that is some function of K as well, then it's actually W1 complete. So you can show it's in W1. And more interestingly is that we can prove very, very strong hardness of approximation results for this problem, which is in the yes case, you can satisfy all the supernodes on the left. In the no case, you can satisfy at most K over n to the 1 over square root K. So this is sub-constant. It's some function of n. No function of K can approximate it. So we can show that solving this really, really large gap, like a very bad approximation parameter, is still W1 hard. And this is what we'll see in tomorrow's talk. And the MaxCover is actually a very important problem and sort of captures very important parameterized complexity questions such as set cover and clique. And we are going to see how these applications come about in the third lecture. So this is sort of more or less what we'll do with MaxCover. So for today, I want to show the first result, that it's W1 complete. So the membership, we have a MaxCover instance, and I want to sort of reduce it to K-clique problem. So how do we do this? So first we introduce, so we think of this graph gamma, and we'll build some gamma prime, which is a graph, and that will be the graph input to our K-clique problem, where the K will be different from this K. So we'll see what it is. So you are first given a MaxCover instance. It's a bipartite graph, and you have supernodes, K supernodes on the right, R supernodes on the left. Then what do we do first? We look at any two different supernodes, Wi, Wj prime on the same side, and introduce every possible edge between them. We do the same for the right on the left side as well. Ui, Uj, Ui prime, introduce all possible nodes between them. So once we do this, then what do we have? We can certainly pick no more than, if you want a clique, you want to pick a clique in this new graph, you cannot pick more than one vertex from any supernode because it's an independent set, right? So you can pick at most one guy from each thing, and you can have a clique of size at most R plus K, because you can pick only one guy from each of them. So there are K guys here and R guys here. Now the nice thing is that if the MaxCover was 1, that means that you have a labeling K guys here, and you can pick one guy in each UI, such that it's a common neighbor to all the K guys. So it forms a biclique. It forms a biclique with K vertices here and R vertices here. And now we have introduced all possible edges between the groups, right? Between the supernodes. So it forms a K plus R sized clique. And you can also show that if the MaxCover was not 1, then you're not going to be able to pick in one. You're going to fail somewhere. So you can get a clique of size at most R plus K minus 1. So this shows that distinguishing and you can reduce a MaxCover instance from parameter k to finding a clique of size r plus k. So if r was a function of k, then this is an FPT reduction, and hence MaxCover is in W1. And in fact, then the question comes, is r, when forcing that r is a function of k, is it reasonable? Well, we just saw that from when we reduced from k clique, the r was really square root k, because it's one side was k choose 2. And if you, in fact, the interesting cases is that when you reduce from ETH and SETH, these fine-grained reductions, even then r can be made a function of k. So what it says is that all these, even this fine subquadratic hardness, when you generalize it to k value, when you bring it over to parameterized complexity terms, then it still is a problem inside W1. So in other words, we showed that MaxCover is a problem inside W1, and we have this reduction, which we'll see tomorrow, which sort of starts from MaxCover with no gap and creates a gap. So it's in some philosophical sense a PCP theorem for parameterized complexity, because you started from a problem inside this class W1 and are able to generate a gap. There are some caveats there, but yeah. So this is the membership, W1 membership of MaxCover. We just saw that it can be reduced to k clique, where k is r plus k now. So yeah. And we saw that it's W1 hard right before, because we reduced k clique to MaxCover. So it's sort of W1 complete. The other problem that I want to really talk about is the one-sided Biclique problem. This is a very interesting problem. And in here, you're given just a bipartite graph, gamma with UW. And you want to find k vertices in W with as many common neighbors. So you want to find k vertices such that you have, like, say, some alpha fraction of the vertices on the left, which are all incident to all these k guys. So you want common neighbors, which is intersection neighbors. So this is the one-sided Biclique problem. And I want to now, this is again a W1 complete problem. And I want to talk about its connections to MaxCover. And in fact, there's a lot of interplay between this and MaxCover that happens. So for instance, here you would want to find these k guys such that they have all these common neighbors. Yeah. So one-sided Biclique can be thought of as a non-colored version. So if you remove the coloring from the MaxCover, where you pick one guy from each supernode. If you remove that constraint that you pick one from each color class, then it's essentially the one-sided Biclique problem. On the other hand, here you are saying in the one-sided Biclique problem, you just want to count the number of common neighbors, whereas there is a notion of covering. That is, if k guys have more than one common neighbor in the same supernode, you still count it as one. So this is the two differences between the two problems. But the nice thing is that one-sided Biclique reduces to MaxCover. You can just use the classic color coding method. You pick large enough colors, and you can de-randomize it using perfect hash families. It's a nice exercise and a nice application of color coding, that you can start from a one-sided Biclique problem, which is here, and you can just color all the W's and all the U's using some, say, f of k colors, and then you're going to get that with some small non-trivial probability that the case where you have k guys here, which covers each supernode, will be reduced to, from one-sided Biclique, you will get a MaxCover instance where you will have all the guys of different color on all of the sides. So you can reduce one-sided Biclique to MaxCover, can be made deterministic. And what about the other direction? Like, is MaxCover equivalent to one-sided Biclique? And the answer is actually yes, but it's extremely non-trivial. It uses a lot of algebraic techniques, and you can show that, yeah, so the issue then would be you're given a MaxCover instance. So it has W1, W2, WK, and you somehow want to reduce it to a one-sided Biclique in which you don't enforce that you pick one guy from each WI. And to make this reduction is very non-trivial, but the answer is yes. They are equivalent under some parameter losses. And the nice thing why I'm talking about one-sided Biclique and MaxCover is that they have very beautiful gap amplification techniques that were developed in the last 4 or 5 years. And they're sort of also contrast one another. They use the fact that in one it's a colored instance, and in the one it's not a colored instance. They use these small nuances to sort of create gaps in different ways. And we're going to see more of this tomorrow. But these are the two problems of interest for tomorrow's talk. So I want to close this before I start talking about coding theory. That in summary, hardness of approximation meets parameterized complexity is this very new exciting area with a lot of open questions, some of which I'll mention in the third talk. And it is very, I can sort of safely say that MaxCover and one-sided Biclique are like the key problems to study. And if you want to prove more new inapproximability results, then you basically have to prove stronger variants of MaxCover and one-sided Biclique in order to prove these kinds of results. So these are the nice objects of study. And now that I've made this definition and I've given some intuition for these problems, when I start creating gap tomorrow, it should be sort of easy to follow. So if you have not been following till now, it's fine. I can ask you completely different questions now. So I want to start with coding theory. And I don't want to introduce it in the way it's sort of done in lectures, because in standard coding theory lectures, because it's not needed for us in that full formality. So I want to start with some questions. So I want to start giving some geometric motivations. So let's look at the Boolean hypercube. It's all strings of length n, where the alphabets you allow are 0, 1. So it's like 0, 0, 0, 0, 1, 0, all these kinds of strings. So there are 2 to the n many strings. Now, if you take any 2 distinct strings, they're going to differ on at least one coordinate, right? So their distance in the Hamming metric, the Hamming metric is where so you're given 2 points in n dimensions, and the Hamming metric basically measures how many coordinates on which they have different values. So if you take any 2 points in 0, 1 to the n that are distinct, their Hamming distance is at least 1 because they differ on at least one coordinate. Good. Now, what about if I say you look at 0, 1 to the n, you look at all the n length strings, but you look at only those ones which have an even number of ones. So if you just look at the even number of ones, that means you look at all 0 string, then all the strings with 2 ones, all the strings with 4 ones, all the strings with 6 ones, so on and so forth. Depending on when n is even or odd, you would either pick all ones or not all ones. And what if we consider this subset? What happens if about any pair of strings within this subset? Now, take any 2 pair of strings. We already concluded that they should differ on at least one coordinate. But now I claim that any 2 strings in the subset should differ on at least 2 coordinates. So that is because if you take 2 strings with the same number of ones, then there are at least 2 different locations where one is 0 and the other is 1, and vice versa. So their distance is at least 2, Hamming distance. And if you take 2 things on with different number of ones, also called different number of Hamming weights, then there's at least a difference of 2, because even, odd, even. So now you have found in this 0, 1 to the n a subset of size 2 to the n minus 1. So it's half the entire space, but their distance is 2, no longer 1. So you have separated them even further. No 2 points are as close as before. They're slightly far now. That was sort of easy. Let's try asking this. What is the largest subset of 0, 1 to the n whose all pairwise Hamming distances? So you want to pick a subset of 0, 1 to the n. So any 2 points in that subset will have distance at least 3. So this is a very non-trivial thing. It's not easy anymore because it's not as easy as picking even things. So you can't just pick every mod 3 because the 2 guys with the same number of ones now need not be at distance 3 or more. So how these things is non-trivial. If if anyone's interested, you can look up what is called the Hamming code. And we know that we can construct really dense subsets of this. Let me now start asking the other way around, which is what is the largest subset of 0, 1 to the n whose all pairwise Hamming distances is at least 0.9n. That means you want to find a subset of n-bit strings. So if you take any two of them, they disagree on 90% of the coordinates. What is the largest set? Okay, so let's try to solve it. So let's take one, and it can be arbitrarily. It can be an arbitrary string, right? Like let's just take some string. So let's call it the all zero string. It doesn't matter. So now the next string you pick in your subset cannot be having less than 0.9 n ones. So it needs to have at least 0.9 n ones. So you pick that, fine. You have now 2 points which are a distance at least 0.9 n. Now any third point you pick still has to be at 0.9 n or more, right? Like the number of ones in it should be at least 0.9 n or more. But if it's 0.9 n or more, then it's the number of ones it has in common with the other thing is at least 0.7 n, right? So you cannot be at 0.9 n from both the new second string you picked and the first string you picked. So the largest subset of 0, 1 to the n, whose all pairwise Hamming distances is at least 0.9 n, is 2. So you can't even pick dense subsets anymore. So you can only pick 2 strings out of the 2 to the n strings whose distance is 0.9 n. So then what about half, like half the points? So like what is the largest subset of 0, 1 to the n whose all pairwise Hamming distances is at least n over 2? So they disagree on half the locations. And here you can look up, again, a very non-trivial construction called the Hadamard code, where you can find n strings out of the 2 to the n strings whose distance is exactly n over 2. That any two strings will exactly have n over 2 things in common and n over 2 things not in common. But it's still n out of 2 to the n many things. What about this? What is the largest subset of 0, 1 to the n whose all pairwise Hamming distances is 0.49 n? So it's slightly less than half. And here we are going to see in the next coming slides that this 0.01 sort of flexibility we have allows us to pick exponentially many points. So you can find, so there are 2 to the n points, and you can find, say, 2 to the n over 100 or something, like some large constant, 2 to the n over 1000 points, which are a distance 0.49 n away. So on 49% of their coordinates, they disagree. And so coding theory, at least the way we will use it, is just to find well-separated point sets. So every pair of points is well separated, but again, it's dense. So that's contradictory properties. We want things to be separated and yet to be dense in the space. And this is what we'll use codes as. It's just these geometric objects that are well separated and dense in some compact space. So now that I tried at least to give some intuition, let me define it formally. So a code is a subset of 0, 1 to the L. So it's L bit strings. And its distance of a code is just, you look at every pair of strings in C, X and Y, and you compute their Hamming distance, which is the number of coordinates on which they disagree. It's a value between 0 and L. And the distance of the code is the minimum over all possible pairs of code words that are in it. A code word is a string inside the code. And a good code, as known, is if you have 2 to the row L. So you have exponentially many strings in C, and their distance is still some constant. So it's delta times L. So it can be at most L, and it can at least 0, but it's at least some delta times L. So if there are some constants, explicit constants rho and L, such that it guarantees that it's dense, it's exponentially many code words, and yet they're well separated, they'll at least disagree on, say, 5% or 20% of the coordinates. So this is a good code, and what we really need is good codes. So as it might be common to most things, random strings are really good codes. and we want to see this now. So if you pick for some small row, you just pick some small constant row, and you pick randomly strings in 0, 1 to the L, and you pick 2 to the row L many strings, then we claim that it forms a code with distance at least 1/4 times L with high probability. Let's see this proof. Take any two random strings in 0, 1 to the L. Now, their expected distance on each coordinate, they can either be 1, 1, 0, 0, 0, 1, or 1, 0. So their expected distance is L over 2. So on half the things they're expected to disagree, and half the things they're expected to agree to be the same. And now you can just put a Chernoff bound and trying to bound the tail and ask, what is the probability that x and y differ in less than L over 4 coordinates, right? So this is the case we don't want. And this is exponential in L. And then you do a simple union bound and over all pairs of strings, and you get that the probability that any pair of strings, if there exists a pair of strings whose distance is less than L over 4, is really, really small. So if you pick 2 to the row L, then with high probability their distance is at least L over 4. So this is the argument for saying why this L over 4 was arbitrary. You could have said anything less than L over 2. 0.49 times L would have been enough. And the nice thing is that there are many efficient deterministic constructions for these random codes. So these are random codes. Obviously, you don't know what is randomness. Randomness is a big question, right? So you might want a deterministic constructions, and there are many efficient constructions which sort of come close to matching this. So whenever I say, whenever in the next few lectures, if I say a code, just think of it as a random string in space. So if a code is just a collection of random strings. And now I want to talk a bit before closing about what is called Reed-Solomon codes. So now we are no longer in the space 0, 1 to the L, but Q to the L, right? And our distance as before is just that if you look at any two strings in Q to the L, so you can write values in 1 to Q in each one of them. And if they disagree on that coordinate, then you look at, they say they disagree, then the number of coordinates on which they disagree is their Hamming distance. But these are no longer on 0, 1, but on Q to the L. So there is this thing called the singleton bound, which is that you cannot be having a large distance and be very dense. Like, so there is some trade-off that happens. That if you want delta of C to be large, then the size of C goes down. So that's the singleton bound. And there are these things called Reed-Solomon codes, which are built using polynomials. So it's all degree D polynomials over FQ, univariate degree D polynomials over FQ. So these are polynomials of the form, say, x to the D plus 3x to the D minus 1, blah, 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 plus 5 equal. This is a polynomial, for instance. So if you look at this polynomial and evaluate it over all of FQ, then that's a string, because the evaluation can be sort of writing on each coordinate. And these codes have amazing properties. That one, the size is large. So the number of degree D polynomials, univariate polynomials over FQ is Q to the D plus 1, because you have D plus 1 coefficients and you can fix any field element for each of the coefficient. And the distance, so you take any two strings in Reed-Solomon codes, they are the evaluation of two different polynomials. Now, if the places they agree, it cannot be more than D. Why? Because if they agree on more than D locations, then you look at the polynomial, which is the difference of the two polynomials. It is still a degree D polynomial, and that will be having more than D roots. And a degree D polynomial cannot have more than D roots, a univariate degree D polynomial. So their distance is Q minus D. On Q minus D of the locations, they disagree, because they can agree on at most D. And if you plug this in, this actually meets the singleton bound. So you have a singleton bound, which is codes can't be, there's a trade-off between how dense they are and what is their distance. And this is sort of saying, yeah, this bound is tight. We can actually find these amazing codes which are both dense and have great distance. So they're well separated and dense in the space. So this is another code we'll be using tomorrow. And so what is tomorrow's plan? I want to conclude today with what tomorrow's plan is. Tomorrow's plan is just to sort of use the codes that we used constructed now, the random codes and the Reed-Solomon codes, and create a gap. And so we'll create a gap for both MaxCover and one-sided Biclique. That's tomorrow's plan. Okay, so that's my talk before the internet goes down again.
Thank you so much, Karthik.